Hello, and welcome to the latest installment of our webinar series. Today's webinar will be designing and optimizing light guides with TracePro. My name's Dave Jacobson. I'm the Senior Application Engineer here at Lambda Research Corporation, and I'll be the presenter. Today's presentation will be a slide presentation lasting approximately 30 to 35 minutes. Before we get started, I'd like to make you aware of some additional resources we have where you can find out more information about TracePro and the capabilities of TracePro. The first is our past TracePro webinars. Roughly monthly we present a webinar on a different topic in TracePro, and we save these webinars and archive the video recordings and slides to our website. And you can go and download these at any time from the webinar section of our website. We also have video tutorials and printed tutorials available on our website where you can go step by step through different product processes in TracePro and how to do different things. Again, these can be downloaded from our website. And then lastly, we offer training classes here several times a year. They're held here at our headquarters in Littleton, Massachusetts, and we have several different topics for these training courses. So if you're interested in finding out more information about training, please check out our website, and we look forward to having you come in and learn a bit more about TracePro. The current release of TracePro is TracePro 7.3.0, and this was released March 7th of 2013. This release can be downloaded by anyone with a current maintenance and support agreement, and you can do that from our website. There's several exciting new features in TracePro 7.3, including a solar utility that allows you to model the sun as it moves across the sky in your model, as well as an enhanced and expanded IES, LDT, or Lambda analysis utility, which features user-configurable lighting reports that you can now download and output from that utility. Let's get started with this webinar, Designing and Optimizing Light Guides with TracePro. The topics for today's webinar, we'll start with a little bit of light guide basics, and we'll talk about some of the features and utilities in TracePro that can be used for designing and optimizing light guides. Then we'll look at using the 3D Interactive Optimizer for symmetric and asymmetric light guide profiles. We'll talk about sweeping a light guide profile along a user-defined path. Then we'll look at the new 3D path option in the 3D Interactive Optimizer that allows you to define a sweep path in X, Y, and Z. We'll also talk a bit about defining variables and optimization targets in the Interactive Optimizer. Then we'll look at setting up the TracePro model and the light sources. And we'll wrap things up with some light guide design tips. So let's talk a little bit about some light guide basics. Light guides typically guide or direct light by total internal reflection, typically abbreviated TIR. The most common materials for light guides would be some type of a plastic or a glass. And the index of refraction of that material of the light guide will affect the coupling of light into the light guide and the light guiding properties of that light guide. In addition, you can apply surface properties to the light guide to change or improve the performance. For example, this could be a roughened surface on the output of the light guide to increase the scattering angle. Now, light guides, I mentioned, guide light by TIR, or total internal reflection. And TIR is when light strikes a material boundary at an angle larger than the critical angle relative to the surface normal and is entirely or totally reflected. And this is a lossless process. Normal to the surface just means at a right angle to that surface. TIR requires that the index of refraction of the light guide material be greater than that of the surrounding material. And if this is not the case, there will be no TIR. I mentioned in a previous slide that a typical light guide material will be a plastic or a glass, so this may have an index of refraction around 1.5. And the typical surrounding material is air, which would have an index of 1, so we would get TIR in a case such as this. Here's a simple model of a light guide in TracePro. In this case, we show a ray coming in here. We have Fresnel reflections off the surface. Then we have the ray being totally internal reflected inside the light guide and then exiting out the other end. Now the critical angle is the incident angle of light, and once again relative to the surface normal, at which TIR occurs. Light at an angle greater than the critical angle is TIR, or totally internal reflected. Light at an angle less than the critical angle will be partially reflected and partially refracted out of the light guide. Now the critical angle varies with the indices of refraction of the light guide material and the surrounding medium or material. Again, typically air for most light guide applications. Now we can calculate the critical angle using Snell's law. And the basic form of Snell's law is N1 sine theta I equals N2 sine theta T, where N1 is the index of refraction of the incident material, N2 is the incident of refraction of the transmitted material, theta I is the incident angle, and theta T is the transmitted angle. And our little graphic down here in the lower right-hand corner shows all those rays, the incident material, transmitted material, and the angles. Now to find the critical angle, we can do that by setting theta T to 90 degrees. And the reason we do that is we're looking to, here's our theta T. We want the ray going this way, so then eventually if it gets higher than that, it actually stays inside of the incident media. So we set this angle to 90. And since the sine of 90 is 1, the equation reduces down to the critical angle is equal to the arc sine of index 2 over index of refraction 1. An example with a typical plastic, the index of the light guide medium is 1.5. The index of the outside medium is 1.0. And the critical angle is the arc sine of N2 over N1, which equals 41.8 degrees. And I do have a small typo here. This should be N2. If we modify our model and we change our angle or incident angle of light to 41.7 degrees, just less than the critical angle, we see the light here is partially refracted out and only partially reflected. In TracePro, by default, the colors of the rays are representative of the flux of the light. So we're starting out red, blue is lower flux, green is in the middle. So this internally reflected ray here is getting lower and lower in power as it goes down. Now if we increase the incident angle so it's slightly greater than the critical angle, we can see here we have the light totally internally reflected inside the light guide. In this case, I limited the number of bounces it would have just to make for a clearer screenshot. Sometimes we want to break TIR. We want to get light to actually get out of the light guide on, say, a specific surface. An example of this might be a backlight or some type of a display ring, say a highlight ring around a switch or a button. There's numerous ways to break TIR, but two of the ones we'll talk about here are adding a surface feature or adding some type of a surface texture. In this example, we added a physical feature to the surface of the light guide, a sort of prismatic type cut in the surface. This could be used in something like a backlight light extractor. In this case, we see here our light is TIR'd, and it's still TIR'd off of our cut feature here. But by changing that, it actually decreases the angle of incident here, which means it's now less than the critical angle, so some of the light is reflected or refracted out of the light guide, and a small portion is contained in the light guide. So we can use these types of features to get light out of a specific surface in a light guide. And we could also add a surface texture. In this case, we have the end of a light guide, and we've applied a roughened surface, say like a ground glass or a sandblasted type surface. And now our light hits the end of the light guide, and it's scattered out in a very large angle. And again, this could be some type of an indicator display or a highlight ring for a button or something like that. Now another topic in light guides is Etendue. Now Etendue is a measure of geometric efficiency. Basically, how much light can you get into a light guide and how efficient will be transmitting it to the other end. The basic formula for Etendue is Etendue, or G, is pi times S, which is the area of the source, the beam, or the optic, times sine squared of the half angle of the beam. Now, another useful option for fiber optics of this equation is Etendue is pi times the area times the numerical aperture of the fiber squared. And a consequence of this conservation of Etendue is that by concentrating the area, the angular distribution of the illumination will spread. For example, this light guide here is a tapered light guide. It starts off, I believe, about 5 millimeters in diameter here and tapers down to about, I think, a half a millimeter here. And we have a relatively collimated beam. It's about 2 degrees beam angle coming in here. And we see, as a consequence of concentrating that down to a smaller area, our angle of illumination is increased. In this case, I think it's about 25 or 26 degree half angle now from our starting 2 degree. So something to be aware of if you're trying to concentrate light down to a smaller point. Should also mention that not all light guides work by total internal reflection. In this case, this is a hollow light guide with a reflective interior made out of a reflective sheet material, say something like an Alinod or an Alcoa product. In this case, the application was a UV or ultraviolet application. And most plastics will have very poor or no transmission in the ultraviolet, especially in the lower wavelengths. So this design used a hollow guide with a reflective material to actually guide the light down. In this case, the light was coming in here, and then it was being output on these 2 ports here. So occasionally you may have a light guide that doesn't use the TIR. Now let's talk a bit about some of the light guide design tools that are available in TracePro. The first is doing 3D modeling right in TracePro itself. TracePro has a CAD engine built right in, doing things primitive solids, blocks, spheres, cones, toruses, as well as Boolean operations, lens elements, reflector elements. These can all be designed and modified right in TracePro. TracePro also has compatibility with most CAD systems, including SolidWorks, ProEngineer, CATIA, Inventor, and numerous others. A lot of times we'll work with models either SAT, STEP, or IGES. So all of these file formats can be imported right into TracePro. So this allows you to do your design work in a CAD system and then just bring the model over to TracePro for analysis. TracePro also features accurate source modeling tools, such as grid sources, surface source properties, and ray files. We've presented a couple webinars on accurate source models in TracePro, so I'd encourage people that are looking to find out more information on making accurate models of light sources to check out those webinars on our website. There are extensive property catalogs included in TracePro. Some of these are including material, surface, and surface source properties. And all of these catalogs are user extendable. So you can add in additional materials or surfaces or surface sources as you're going along and have those available for all future models. And we also have the TracePro utilities. These are things like our IES LDT or LUMDAT analysis utility that I mentioned earlier. Allows you to create user configurable lighting reports. Our surface source property generator utility allows you to make a new surface source property from the graphs such as the spectrum and the angular distribution graph you might find, say, on an LED datasheet. We have a texture optimizer. This allows you to optimize the texture, say, on a backlight for a computer screen. You can optimize the distribution of that texture to provide for uniform illumination towards the viewer. And then we have our 2D and 3D interactive optimizers. The 2D and 3D geometry modelers. Now this is something new that we've added into our TracePro LC version. This is starting with the new TracePro 7.3 release. We've added 2D and 3D geometry modelers. Now these geometry modelers in TracePro LC have the same geometry creation capability as our current interactive optimizers, the 2D and 3D interactive optimizers, but they just lack the optimization feature. So any geometry that we can create that we'll show during today's webinar can also be done in TracePro LC now with the 7.3 release, but you just won't be able to do the automatic optimization. Then our 2D and 3D interactive optimizers, now those are available in our TracePro Standard and TracePro Expert editions. Today's webinar, we're going to focus for the most part on our 3D interactive optimizer and how you can use that for light guide design. Now to open the optimizer, you just go to the Utilities menu in TracePro and scroll down to 3D interactive optimizer. And when you do that, you'll see three main windows when you launch the optimizer: the surface list, the object view, and the property editor. We'll just go through a little bit about what each of those windows does. The surface list allows you to define the type of surface, the shape, or the profile that we're going to use as our starting point. And the options here are planar, a B-spline surface, a parameterized surface, a 2D profile, or a path. Going a little bit further into those drop-downs or menus, the options for a B-spline surface are a free B-spline, a B-spline that's symmetric across the x-axis, a B-spline that's symmetric across the y-axis, and a B-spline that's symmetric across the x and y-axes. We can also do a biconic surface under the parameterized surface. The 2D profile allows us to do an asymmetric profile, a symmetric profile, or an elliptical profile. And then lastly, our path can either be a 2D path or a three-dimensional path. After you've defined your surface shape, the next step is to turn it into a solid object. And this is done in the Objects window. Our choices here are radially symmetric, extrusion, lens, sweep, and biaxial. Now I have radial symmetry, extrusion, and sweep bolded here. Those are the ones we're going to look at during today's webinar, probably the ones that are most useful for a light guide type design. And then the last of the three main windows is the property editor. And what you see here is going to vary depending on what you have selected in the other windows. If you have a segment selected or a spline, it'll tell you the segment type. It'll allow you to apply a surface property, such as a mirror property or a scattering property to it. And the optimizer uses your TracePro property database that's already existing on your computer. So any property that you've added or that's in the default catalogs is available for use in the optimizer. We can also turn a surface into a reflective surface, as well as make it a Fresnel type surface. If you're working in the object window, then the selections here in the property editor change. We can choose the origin of where the object's going to be inserted, any tilts, the thickness. In this case, this is an extruded application, so we could determine the thickness on how far that will be extruded. We can choose a material property, once again from the TracePro properties database that will be already installed on your computer. Draft angle for the extrusion, as well as we wanted to set just a default refractive index for the model just in the model view. Well, now let's take a look at a couple examples of different types of geometries that we can do using this 3D interactive optimizer. The first we'll look at is radial symmetry. And in this case, we define our profile. Now, because this is symmetric, any of the points we place on this side of the axis are mirrored over here. So we just really are defining one side of our profile, and then that's mirrored across the axis. Now in this case, this is a little like a highlight ring. Say there'll be a button sitting here in the center. I also want to cut out the center section. I want to have room for this to fit around my button or my indicator. So I add in an additional feature. And I'll use this to actually cut out that hole in the light guide when I send it over to TracePro. Now here's the two objects in the object view. I've chosen radial symmetry here. So it's just revolving that profile around. And here's my light guide profile. And here's that center cutout portion that I'm going to use. And then the last step before I send the model over to TracePro is I add in one command line here in the after scheme editor in the optimization dialog. And basically I'm saying subtract object 1 from object 0. So I'm subtracting that little centerpiece from the main light guide. And here's the results in TracePro. We can see our profile, as well as we can see here's the hole cut through the center by that small profile second profile that I added in. Now that was a symmetric type of profile. In this case, this is an asymmetric profile. And for this light guide, we're using splines and segments. And in this application, our light's coming in this way. And we have 2 exit ports. Could be some type of an indicator, say. And we define our straight segments. And then these bend radii here are done using spline segments. And here's this blue dot, in this case, is a control point. And once we put that in, we can move that around anywhere we want and dynamically change the shape of this model in real time. Now to make a solid object from that profile, I used an extrusion in this case. This is in the object view window. And I set my type to be extrusion and my thickness to be 5 and a draft angle of 0. And I now have a 5 millimeter thick light guide. Now another way of doing that same type of a light guide would be to use a symmetric profile and sweep paths. So what we're going to do here is we're going to define one leg of the light guide. And going back one slide here, if we look at this light guide, it can actually be considered almost 2 different parts. We have one light guide here and one light guide here, and then they're just combined together. So for doing this with sweep paths, we're going to define the profile of one leg. In this case, this is 5 millimeters by 2.5. So when I add the two legs together, the end of my light guide, or the entrance end of my light guide, will be 5 millimeters by 5 millimeters. Then the next step is to define the sweep path. In this case, that profile will be swept along this segment. In this case, I have a spline segment here. It's set nearly straight now with 3 control points, and then making a right turn coming out here. This is for one leg. I repeat that process for the second leg. In this case, this is a slightly longer sweep path, so this is the longer leg of the light guide. And I go into the object view again, but now I set my type here as a sweep. And I can see here where I've expanded it out, I'm actually sweeping surface 0, that's my profile, along path 1. And that'll create this lower leg of the light guide here. And I can repeat that process for the upper leg. In this case, I'm still using that same profile, using it a second time, but now I'm going to sweep it along a different path, path 2. And one last step before sending this model over to TracePro is I add in a little macro command here, just saying unite those two objects. So it'll turn it into one single light guide. And we'll come back to this example here in a little bit to show setting up some of the optimization for this as well. Now, a new feature in TracePro 7.3 is the ability to define a 3D sweep path. So we can take this light guide profile, but now we can define a 3-dimensional sweep path in X, Y, and Z, and we'll sweep that profile along that path. So it gives you an extra degree of freedom for your sweep paths. The procedure for making the object is the same. We choose our sweep type, we choose the surface, the profile that we're going to use, and then the path. And when I send that over to TracePro, here's the resulting light guide swept along a 3D space. And now let's walk through what you could do to set up sort of a basic optimization, some of the steps that are required. And I'm going to go back, as I mentioned, I'm going to use my light guide example where I was sweeping a profile along 2 paths. And I want to optimize these bends here. Now initially I've set them to sort of a worst case, just a straight line, almost a 45-degree angle for these bends. And my goal is to optimize the bends in the light guide for equal light at both of these outputs, as well as the best efficiency that I can get. Now if I run this model as is, and I'm using just a 1-watt source, we can see on leg 1 we have 0.143 watts, leg 2 0.164 watts. So roughly just a little bit over 0.3 of a watt, or just over 30% efficient. And the uniformity between the two is not too bad, probably plus or minus 5% or so. But we'd like to see, can we actually improve that efficiency? I'd like to see more light actually getting out of this light guide. So my first step is to set up optimization variables. And I'm going to use the spline control points as my variables. And if we look here, this dotted line box around the control point is the range of motion that variable is defined as. And we can see here we have plus or minus 6 millimeters for the y-axis and plus or minus 3 millimeters for the z-axis. So this point here is going to be able to move anywhere within that box. I've also done similar for the other 2 control points here. I just haven't shown the actual values. If we look at our second leg, we've done the same thing. We have 3 control points, and we've defined the range of motion for these variables. And that's shown by this dotted box around there. In this case, I'm showing one of the outer ones, and now this one's only being allowed to move plus or minus 3 millimeters in both the Y and Z axis. So I have the center control point moving a larger amount than the outer control points. So our next step is to set the model up in TracePro. What I've done is I exported the geometry I created here in the optimizer to TracePro, and I've added a few features. I've added a light source, and I've added 2 targets here. And my light source in this example, I used a surface source property from the surface source property catalog included in TracePro, and I chose for this example just a Cree XPE white LED. And I applied that to the surface of this little block that I'm using to represent the LED. Now I also defined 2 targets, and these are simple blocks that I inserted in TracePro, primitive solids. But one thing I did is I named the surface, this surface here that's facing the light guide. I named one detector 1, the other one detector 2, so they have unique names. And we'll use that as part of the optimization process. Now to set up the optimization, in this case what I'm going to do is if you remember I mentioned I'm starting with a 1 watt source. So to have equal light on both sides, I'm going to set my target value at 0.5 watts on each of the 2 detectors. And I'm doing what's a flux operand. Some of the other options are irradiance profile, candela profiles, uniformity, CIE coordinates. So there's numerous types of optimization operands that you can choose. And I mentioned in the previous slide I named my 2 surfaces, detector 1 and detector 2. So this is how the optimizer knows where to look for the flux values and the irradiance maps in the model. It's going to look for the one on surface detector 1 and also the one on surface named detector 2. And that's why it's important to give these unique names so that it knows and it looks on the correct surface. Now the way the optimizer works is it takes that model, our starting model, sends it to TracePro, runs the ray trace. TracePro does the analysis, in this case looks at flux values, sends that back to the optimizer. The optimizer compares that to the goal or our target, changes the model, sends the updated model back to TracePro, repeats that whole process. And the results here for this light guide optimization, it did that 919 times. It found the best result at iteration 483. And here's our error function. So the smaller this gets, the closer we are to our target. And we see here, really after about 250 or so iterations, it was just trying to improve the solution around what was probably pretty close to the final answer. And here's our sweep paths after optimization. Leg 1, it's still somewhat straight, but it does have some radii added here for the 2 control points. And the second one is more semicircular, much different than what it looked like before. Here's that model then sent back to TracePro. We can see the changes in our profiles. To make it a little more obvious, the obligatory before and after picture. The red traces here, the red portions are what the light guide looked like when it started. And then the blue profile is the result after the optimization was run. And then here's the results. Leg 1, 0.355 watts, leg 2, 0.392, so roughly 0.75 watts getting out of this light guide compared to the 0.3 watts. So we went from 30% efficiency to 75% efficiency. And we can also see our uniformity from leg to leg is roughly plus or minus 5, plus or minus 6%. So, there might be some room for improvement there as well. One thing we could do if we wanted to see, is this the best solution? We could go back to our initial condition and make a change. Start from a different point, make this less straight or more curved than what it winds up. Rerun the optimization, see if it converges to about the same answer. You may find a slightly better answer, or it may just converge right back to where this is at now. So let's wrap this webinar up today here with a few light guide design tips. These are just some basic tips for doing light guide design. First is avoid sharp corners. The second will be to keep the light guide bend radii as large as possible. And really these first two items are basically, the goal there is to keep the light inside the light guide, to maintain that TIR. So by doing that, by avoiding sharp corners and keeping the bend radii large, you can make it so that that light is always above the critical angle and stays inside the light guide. Also, it's important, I believe, to use an accurate source model. Now, the more accurate your source model, whether it's an LED or a fluorescent lamp or an arc lamp, the more accurate the results are going to be. This could be, say, using a ray file. You could download a ray file from an LED manufacturer. That can be used as part of the optimization process. Or a surface source property in TracePro with the angular and spectral distribution of the source. To improve efficiency and keeping the light inside the light guide as much as possible, use scattering surface only where necessary. So really only apply scattering to your output surfaces if that's the way this light guide is going to work. It's also very important to trace enough rays to get an accurate answer. This is both during optimization and in the final analysis. If you're trying to do a uniformity from a light guide and you're only tracing 1,000 rays and say only 200 or 300 are making it to your target, it's going to be very hard to determine, is that really a uniform distribution. So typically you're looking at tracing large amounts of rays to get accurate answers, especially when you get into things like uniformity and irradiance profiles. Also, we like to have people use the interactive optimizers. And when you do that, make sure you define enough variables so you give it a range of freedom to optimize to a solution. This example I just showed, there was 6 variables defined, 3 control points for the splines on each of the legs. And if necessary, you can use multiple optimization operands. So in this case, I just defined a flux. But if I was also looking for uniformity across the output surface, I could define a uniformity operand or a specific irradiance profile as well as a flux target, or a candela profile where I want to see a specific angular distribution. And then lastly, use the analysis tools in TracePro to verify your results. Things like the irradiance and the illuminance maps to look at the spatial distribution of light. Use the candela plots to see the angular distribution. What kind of angles is that light coming out of the light guide at? We can also use the luminance and radiance plots, and this can be used to how would this look to a viewer or to a camera. And ideally, you'd want to set up multiple eye positions. So say for a light guide like the one I just showed, you may set up a luminance map looking straight into the light guide. But you may also set up another one 45 degrees off axis. So what would the light guide look like to an off-axis viewer as opposed to somebody's looking at it straight on? And you can also use path sorting to see different ray paths in TracePro, as well as to see where rays are hitting a specific area of the irradiance map. Where are those rays coming from? So a lot of path sorting and ray sorting options available in TracePro. I'd like to mention that as we wrap this up, a recording of this webinar and a copy of the slides are available in the webinars section of our website, as I've mentioned before, along with all of our other past webinars. lambdares.com, and just go to the webinars section there. So with that, I would like to thank everybody for attending today. And if you're looking for any additional information, please feel free to contact us here at Lambda Research Corporation. We're in Littleton, Massachusetts. Our number is 978-486-0766. Our website, www.lambdares.com. So thank you, and we look forward to seeing everybody again in our future webinars. Have a good day.